Hello and welcome. Over the next few minutes, I'm going to try to explain in mathematical terms one of the fundamental facts of life, and that is why rocks are heavy. Now, anyone who's ever lifted rocks probably has a pretty good idea that rocks are heavy, but most people do not develop a good, solid intuition into exactly how heavy rocks really are. And so what I'm going to do now is I'm going to try to lay out in mathematical terms exactly why it is that rocks are heavy. Now, the weight of a rock can be calculated using the very, very simple formula. Weight is given by density times volume. Now, there are several complications in this conversation that we're going to try to avoid. First of all, the density of a rock is not uniform. If you find a rock out in the field, it'll be more dense in some parts than others. But we're going to just assume, for the sake of this conversation, that the density of our rocks is uniform. The next thing that we're going to have to consider is the fact that the density of the rock will change from one sort of rock to another. And some rocks are incredibly dense and some are considerably less so. There are rocks that float, in fact. They're so light. So the question then becomes, how dense is a rock? And of course that's going to depend on which rock, on what kind of rock, and exactly which one. But in general, the density of a rock is going to range somewhere between 100 pounds per cubic foot to maybe 200 pounds per cubic foot. I believe if you look at something like a nice hard granite, that one will weigh somewhere in the 150 to 170 pounds per cubic foot range. So for the purposes of this conversation, we're going to assume that that density right there, that density is equal to 150 pounds per cubic foot, and we're going to assume also that the rocks we're discussing are all uniformly dense. And so then the question becomes, how heavy is a rock? Well, at that stage, it literally is just a question of what the volume of that rock is. And what we'll find is that our formula becomes that the weight of the rock is given by 150 times the volume of the rock. And so now we're going to have a couple of examples. We're going to take a look at a couple of examples. The very first thing I want you to think of is the simplest possible rock. It would be a 1 foot cube. So we're talking about a 1 foot by 1 foot by 1 foot rock. It's about this big. You might find one laying in your yard. Not hard to imagine what that rock would look like. Of course, if the volume of the rock is 1 by 1 by 1, that is a 1 cubic foot rock, the weight of the rock is going to be 150 pounds. That fact alone tends to surprise a lot of people. Ask someone how much a 1 foot cube rock would weigh, most people will tell you 50 pounds, maybe 60 pounds. They usually dramatically underestimate that. So, roughly 150 pounds for a 1 foot by 1 foot by 1 foot rock. Now let's think for a second about what happens as that rock grows. So let's double the size of it. We're now thinking about a cubic rock that is 2 feet on a side. That is 2 foot by 2 foot by 2 foot. The interesting thing about this particular rock is that its volume, we can determine it is 2 times 2 times 2. That is 8. The volume of this particular rock is 8, and therefore the weight of this rock is going to be 150 times 8, which happens to be 1,200 pounds. Now that is a considerably heavy rock. I want you to slow down and think about that for a second. A 2 foot by 2 foot rock, 2 foot cube rock is really only about this big, and yet it's going to weigh 1,200 pounds if it's granite. Very, very heavy. Okay? Now let's take this up another step. We're going to let this rock grow to 3 foot cube. A 3 foot cube rock is going to have a volume of 27 cubic feet, and therefore the weight of that particular rock is going to be given by 150 times 27 cubic feet. Now, 150 times 27 is a relatively large number. 100 times 27 is 2,700. 50 times 27 would be half of 27. That's 1,350 with a couple extra zeros. So we're talking 2,700 plus 1,350. That should be a 4,050 pound rock. That, my friends, is more than most cars weigh. A good-sized minivan usually weighs around 4,000 pounds, and yet this rock is really only 3 foot by 3 foot by 3 foot, probably smaller than the reclining chair you have sitting in your living room. You're not going to move that rock. That rock is ridiculously heavy. So let's talk for just a moment now, if you will, about why it is that these rocks' volumes grow so quickly. This comes down to the fact that the volume is measuring something that is three-dimensional. And so as the object grows proportionally, the growth rate, the ratio of similarity between the original and the new one, is going to be tripled when we look at the impact that it has on the volume, which is to say, if we double the size of the thing, that times 2 will then get cubed. It will become 8 times the volume. If we were to multiply the thing by a ratio of 10, so scale it up to 10 times the size that it used to be, that will actually take its volume up to 10 cubed, to 1,000 times its original volume. That, as a function, is just the function x cubed, which we all know grows very, very quickly. It grows much more quickly than a linear or a quadratic function, and therefore the volume portion in this calculation is going to grow really, really quickly. One interesting thing about this three-dimensional measurement that you will find is that every single volume formula that you know is always going to have 3 variables in it. You can look at something like the volume of a cube, or, and for that matter, a rectangular prism, which would be given by a length times a width times a height. You'll notice that as a polynomial, the degree of this formula right here is 3. It has 3 different variables going into it. We could also look at the volume of a cylinder, which we might know to be pi r squared h. I see 2 r's and 1 h. There are 3 variables going into this, because this is a 3-dimensional measurement. We are measuring something fundamentally 3-dimensional here. The volume of a cone you might know to be 1/3 pi r squared h. The volume of a sphere we know to be 4/3 pi r cubed. All of these volume formulas, and for that matter, every other volume formula you could possibly come up with, will be a degree 3 polynomial because it is measuring something of degree 3. Because of that, if that particular dimension changes, each copy of that variable in there is changing by the same ratio as the object scales up, which means that the 2 that would be going in is going to be cubed. So for instance, if we had a particular sphere with a radius of r, then when we doubled that, it would become a sphere with a radius of 2r, but that 2r is going to end up inside the parentheses here. It will then get cubed, and therefore the 2 gets cubed and the r gets cubed. That ends up being 4/3 pi times 8 times r cubed, which we can rewrite as 8 times the original volume of the cube, sphere, the original sphere. So as I was saying, each of the volume calculations involves a degree 3 polynomial. Every time you scale up such an object, each one of the dimensions there will scale up by the same factor, and so the impact of that scale factor will then get cubed. That tells us then that the volume will grow at the cube of the scale factor. Hence, when the rock goes from being a 1-foot cube to a 3-foot cube, the volume increases not by times 3, but rather times 3 cubed, which is 27. And the weight increases proportionally. So, that being said, the reason that rocks are heavy as they grow is that the volume grows. The volume grows much, much more quickly than most people expect. From a practical point of view, this is interesting, but really the most important thing you need to take away from this is that as rocks get beyond the 1 to 2 foot in each dimension range, they become so heavy so quickly that you really, really cannot reasonably lift them. In fact, you don't want to try to lift them. If you try to lift a rock that is 3 foot by 3 foot by 3 foot, you're almost certainly going to just hurt yourself and you will not get it off the ground. Now, that is not to say that you can't move a rock. You could move it with a crane, or you could move it with a backhoe or some other piece of large equipment. In fact, you could probably move almost any size rock with a large enough lever. That is exactly how you do it, except when you lever a rock, you don't want to stick the lever up under there and crank it down thinking you're going to lift the entire thing up off the ground. All you want to do is lift it up just enough that you can stick another rock or a log or something up underneath it to hold it there. And then you adjust your lever and you do it again. You crank it up another 3 or 4 inches and you prop it in place. And then you crank it up again. And after 10 or 15 iterations of this, if you're lucky, you manage to tip the rock over. Bang. And congratulations, 2 hours later, you've now moved your rock 3 feet. So yes, rocks are very heavy. They're incredibly difficult to move, and you should never underestimate them, or you could hurt yourself. So hopefully this is helpful, and hopefully you now have a slightly better intuition as to exactly why it is that rocks are heavy.